10 billion light years from where you are right now, there is a shadow with a name. Astronomers call it TON 618, and it is a single object, one object that weighs as much as 66 billion of our suns. When Hiram Spinrad and his team first measured it in 2004, the number came back so large that most of them assumed the instrument had made a mistake. It had not. If you could take our entire solar system from the Sun all the way out past Pluto and place it inside of TON 618, our whole solar system would disappear like a single grain of sand dropped into the ocean. And yet, for all that mass, it gives off no light of its own. It is as close to true darkness as anything we have ever found. If you love drifting through the strange corners of the cosmos with us, hit that like button and subscribe to Cosmic Drift. Now, let us drift together toward the heaviest shadow in the universe. Section 1. The Weight of Silence. The thing about a discovery like TON 618 is that it did not arrive with a bang. There was no moment in a control room where someone stood up and shouted. There was no press conference the next morning. There were only numbers on a screen and a long, quiet pause, while the people looking at those numbers tried to decide whether they believed what the numbers were telling them. That pause, in a sense, is where this whole story begins. Not with the object itself, because the object had been sitting there in the sky for 10 billion years before any human noticed it. It begins with the silence that followed the first real measurement, and with the slow, careful work of checking and rechecking and checking again. Spinrad's team was not looking for a monster that night. They were doing what astronomers often do, which is to say they were pointing their instruments at faint lights in the sky and asking those lights patient, respectful questions. What are you made of? How fast are you moving? How far away are you? How bright would you be if we stood beside you instead of 10 billion light years away? These are old questions. They are the questions that astronomers have been asking for centuries, and the answers usually come back in familiar ranges. A star weighs somewhere between 1/10 of our sun and a few dozen times our sun. A galaxy weighs a few 100 billion suns, mostly in the form of the stars that fill it. Even the black holes at the centers of galaxies, the ones that scientists had been studying for decades, fell into a known range. A few million suns for a quiet one. Maybe 1 billion suns for an extreme one. 1 billion was already considered the edge of the map. 1 billion was the kind of number that made astronomers use the word supermassive and feel like they had stretched the language far enough. And then the instrument returned a number that was 66 times larger than that edge. 66 billion suns. Not a galaxy, not a cluster of stars. One single gravitational well. One point, so to speak, though of course nothing this large can really be called a point. One object hiding inside a quasar that had been catalogued decades earlier, quietly weighing more than most of the galaxies that humans had ever measured. There is a story that one of the graduate students working on the data looked at the screen, looked away, and then looked back, as if hoping the number would have changed while he was not watching. It had not. It stayed where it was patient, the way all truths in astronomy eventually become patient. The sky has no reason to hide anything from us. The sky has been sitting there for billions of years, holding its secrets loosely, waiting for a species with good enough eyes to finally notice. To understand why the number was so shocking, you have to understand the gentle rules that astronomers had built for themselves over the preceding half-century. There was a rough ceiling on how big a black hole could become. The logic went like this. A black hole grows by eating. It eats gas, it eats dust, it eats the occasional unlucky star. But a black hole cannot simply swallow everything around it all at once. When it pulls matter in, that matter falls inward, heats up, and begins to shine. And the shine of falling matter produces a kind of pressure, a pushing outward, that works against the pulling inward. If the pulling is too strong, the shining is too bright, and the shining pushes new matter away before it can fall in. This is called the Eddington limit, and for a long time, it was thought to set a practical ceiling on how quickly a black hole could grow. With the Eddington limit in mind, you could do the math on how long it would take starting from a small black hole in the early universe to grow to some enormous size. And the math kept saying that 10 billion suns was hard, that 100 billion suns was almost impossible, that 66 billion suns in a universe that had only been running for a few billion years at the time. The light we see now was emitted should not exist. But there it was. This is one of those quiet little puzzles that I want you to carry with you for the rest of this drift. Ton 618 should not have had enough time to become as large as it is. The universe, when the light we see from Ton 618 was first emitted, was still quite young. It was a universe of hot gas slowly, cooling of the first generations of stars, only just beginning to die of galaxies still forming and still colliding with each other in ways we would recognize today. And in the middle of all of that tender early cosmic weather, there was already a single object weighing 66 billion suns. We will come back to this puzzle later because it has a partial answer, and the partial answer is itself fascinating. But for now, just hold the shape of it in your mind. A monster already fully grown in a universe that was still learning how to walk. Hiram Spinrad, the astronomer leading that team, was not a showman. He was a careful man with a long career behind him. He had spent decades measuring the redshifts of distant objects, which is to say, he had spent decades working out how fast the universe was stretching and how long ago the light from any particular object had begun its journey. Redshift, if you have not encountered it before, is simply the way light from a moving source gets stretched. If a source is rushing away from us, the waves of light coming from it get pulled longer. Red light has longer waves than blue light, so light from fast-moving objects appears redder than it would if the object was sitting still. The more redshifted the light, the faster the object is moving away from us, and because the universe is expanding, the more distant it must be. Spinrad had built much of his career on measurements like this. He knew how to squeeze the last drop of information out of the faintest smudges of light. And the faint smudge of light, that is Ton 618, gave him a redshift so high that the object's light had been traveling toward us for something like 10.5 billion years. That is almost the full age of the universe. When the photons that reached his telescope first left the neighborhood of Ton 618, the Earth did not yet exist. The Sun did not yet exist. Our galaxy was still assembling itself out of smaller galactic pieces. Life, whatever life would eventually mean, was nowhere in the cosmic story yet. Those photons traveled through 10.5 billion years of expanding space across dark voids between galaxy clusters, past quasars and protostars, and supernovae, and the slow birth of every element heavier than iron. And they arrived finally on a clear night on a mirror attached to a telescope in a dome on a mountain, where a human being and an instrument together performed the small miraculous act of noticing them. The first thing the team noticed was how bright the light was. Quasars are always bright. That is in the name itself. Quasar is short for quasi-stellar object, which is what astronomers called these things back in the 1960s, when nobody knew exactly what they were. They looked like stars. They were points of light unresolved, even in the best telescopes of the era. But their spectra, the fingerprint of colors in their light, did not match any known star, Their spectra matched distant galaxies, but the light was far too bright to be coming from a galaxy that far away. For a while, nobody could make it fit. And then slowly, through the 1960s and into the 1970s, the answer became clear. These things were not stars at all. They were the centers of distant galaxies, galaxies so far away that the ordinary light of their ordinary stars was lost in the background. But at the center of each of these galaxies, something was generating an extraordinary amount of light. Something small because the light could flicker and change over a few months or a few years, which meant the object producing the light could not be any bigger than a few light months across. Something hot, because the spectrum of the light was consistent with gas at extremely high temperatures. And something massive, because nothing else could hold that much bright hot gas in one place without blowing it apart. A black hole, in other words. A very, very large one. Ton 618 is the quasar powered by the black hole. The black hole is the engine. The quasar is the light that the engine produces as it feeds. When Spinrad and his team measured Ton 618's light, they were not measuring the black hole directly. They were measuring the light of the hot gas falling toward the black hole, but from the width of certain spectral lines in that light, which broaden in a very specific way, depending on the gravitational pull of the thing at the center. They could work out the mass of the thing at the center. And the thing at the center, the engine, the gravitational monster, that was drawing in all of that gas and making it scream with heat and light, weighed 66 billion suns. Let me sit with that number for a moment. Not the number itself, but what it means. Our sun, as you probably know, is already very, very heavy. Heavy enough that its own gravity crushes the hydrogen at its center into helium, releasing the energy that we feel on Earth as sunlight. Heavy enough that the Earth at a distance of 93 million miles remains held in its orbit year after year without ever drifting away. Heavy enough to hold the outermost planets of our solar system in place billions of miles farther out than Earth, locked into their own slow, patient orbits. The sun is heavy by any ordinary human standard. It weighs roughly 2 nonillion kilograms, which is a 2 followed by 30 zeros. Now put 66 billion of those side by side. If our sun were a grain of sand, Ton 618 would be a beach, no larger than a beach, a sandbar, stretching from one horizon to the other, an entire desert. If you gathered every star in our Milky Way galaxy, all 400 billion of them, and you weighed them all together, you would get something roughly 10 times heavier than Ton 618. But those 400 billion stars are spread out across 100,000 light-years of space. Ton 618 is all in one place, or rather, all in what we might in a moment of loose language call one place, because the rules of space and place themselves start to bend inside something like this. There is a word for black holes in this range. Astronomers call them ultramassive. They distinguish them from the merely supermassive black holes that sit at the centers of most large galaxies, including our own. Our own galaxy's central black hole, Sagittarius A star, weighs about 4 million suns. That sounds enormous, and it is enormous by any human standard, but compared to Ton 618, it is almost trivial. If Sagittarius A star were a single person standing on the Earth, Ton 618 would be more than 10,000 such people stacked one on top of the other. The ultramassive black holes are rare. We have found only a handful of them scattered across the observable universe, and even among those handful, Ton 618 stands at or very near the top of the list. Some measurements made with different instruments and different assumptions have come back even higher. Some suggest Ton 618 might be closer to 40 billion suns, rather than 66. Others suggest it might actually be closer to 100 billion. The number we have is not a certainty. It is an estimate, and the estimate carries genuine uncertainty because measuring the mass of an object 10 billion light years away is not like measuring a bag of flour in a kitchen. But whatever the exact number is, the point is this. Ton 618 is one of the heaviest single objects we have ever been able to measure in the known universe. It is not heavy for a black hole. It is heavy full stop. It is at the outer limit of what reality, as far as we currently understand, it seems to allow. And now comes the part that to me is the strangest part of all. This enormously heavy object gives off no light. Let me explain what I mean, because I know it sounds like a contradiction with what I just said about quasars being bright. The quasar is bright. The quasar is the brightest kind of object we know of in the universe. Some quasars shine more brightly than all of the stars in their host galaxy combined many times over. Ton 618. The quasar is shining with the light of something like 100 trillion suns. If you could see it with your naked eye from a comfortable distance, say a few hundred light years away, it would be blindingly, unbearably bright. You would not be able to look at it. You would not be able to stand on a planet in the same solar system as it. Every atom of your body would be stripped apart by the radiation. The quasar light is real. The quasar light is one of the most violent and intense things that nature produces. But the light is not coming from the black hole. The light is coming from everything around the black hole that is falling in. The black hole itself, the actual gravitational monster at the heart of all of this, is dark. It is darker than anything you have ever seen. It is not like a dark room where you could still sense the faint glow of a distant street lamp. It is not like a moonless night in the country where the stars would still reach you. It is a darkness so complete that no photon, once it crosses the black hole's outer boundary, can ever travel back to tell us what it found. The light that we see from Ton 618 is entirely made of things that are still on their way in. Everything that has already arrived is silent. This is the strange inversion at the heart of our story. The brightest engine in the universe is powered by the darkest thing in the universe. The light is real, but it is the light of a long, slow falling. It is the last flicker of everything that has ever wandered too close. And behind all of that light waiting, patient, unreachable, is the heaviest silence we have ever found. I want to pause here on the word silence, because I have been using it loosely, and I want to use it now with a little more care. A black hole is not silent in the ordinary sense. Space itself has no medium for sound. There is no air to carry vibrations. So in that sense, nothing in space is audible, and silence is the default everywhere. But the silence of a black hole is a different silence. It is a silence of information. When something crosses the event horizon, the outer boundary of a black hole, it becomes from our perspective permanently unreachable. Not just hard to reach, not just far away, permanently in principle by the laws of physics, as we currently understand them, unreachable. Nothing it does after that point can ever reach us. No light it emits, no signal it sends, no message, no matter how loud. The information is not destroyed, not in any simple way, but it is sealed off. It is behind a one-way door. And on this side of the door, all we have is the faint hot light of things that have not quite arrived yet. Ton 618 is a door 66 billion suns heavy, closed, locked, with no key on our side. And the light of the quasar, the 10 billion year old light that reached Hiram Spinrad's telescope in 2004, is the sound of everything that has been lining up at that door for longer than our planet has existed. Now I want to return to something I mentioned earlier, the distinction between massive, supermassive and ultramassive. These are not just levels of the same thing like small, medium and large. They are in some ways different categories of object. Stellar mass black holes, the smallest kind, are the leftovers of dying stars. When a star much larger than our Sun runs out of fuel, its core collapses, and if the core is heavy enough, it collapses all the way down into a black hole. These little black holes weigh between a few times our Sun, and at the very top end perhaps 100 times our Sun. They are common. The Milky Way probably contains millions of them scattered through the disk, going about their quiet gravitational business. They are the products of stellar death, and they fit within a well-understood chain of physics, from the fusion in a star's core to the supernova that ends the star's life to the remnant left behind. Supermassive black holes are different. They are millions to billions of times our Sun. They sit at the very centers of galaxies. They seem to have grown along with their galaxies in some intimate, tangled, not yet fully understood coevolution. The mass of a supermassive black hole is correlated with the mass of the central bulge of stars in the galaxy that contains it. Bigger galaxies have bigger central black holes. Smaller galaxies have smaller ones. This relationship is so consistent that astronomers use it as a rough predictor. If you can measure the central bulge, you can guess the black hole. We do not yet have a complete theory for why this should be so, but the correlation is real and strong. Supermassive black holes and their host galaxies are somehow linked, growing together, regulating each other, maybe even helping each other form in the first place. And then there are the ultramassive, the ones above 10 billion suns. These are in some sense the ones that do not quite fit. They are too big for the standard story. Even allowing for the most generous assumptions about how fast black holes can grow, it is difficult to get to 40 or 50 or 66 billion suns in the time the universe has available. Unless, and this is one of the leading ideas, the seeds of these ultramassive objects were themselves already large. Not the collapsed remnants of individual stars, but the direct collapse of enormous clouds of gas in the very early universe, which would have produced seed black holes of already tens of thousands or hundreds of thousands of suns. If that is what happened, then the monster at the heart of TON 618 was born massive and has only grown from there. But even with head starts like that, the growth rate required to produce something like TON 618 in the available time is extraordinary. For long stretches of its life, this object must have been feeding at or near the maximum possible rate. It must have had an extraordinarily rich supply of gas and dust around it. It must have existed in a part of the universe where galaxies were colliding and merging, funneling new material down to the center over and over again. And all of that feeding is what we are seeing now as the light of the quasar. The 10 billion-year-old glow of an object gorging itself on its surroundings, growing, 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 and then eventually running out of things to eat and going quiet. Because that is the other part of this story, though we will come back to it in more detail later. A quasar is not forever. The light of TON 618 that we see now is the light of its feeding phase. But feeding phases end. When the accessible gas runs out, the quasar fades. The black hole remains, of course. It does not go anywhere. It sits in the center of its host galaxy, vast and dark, waiting for the next galactic collision, the next fresh delivery of gas, the next chance to flare briefly back to life. For most of its existence, a black hole the size of TON 618 is probably quiet. It is probably not a quasar. It is probably just a heavy, silent presence at the middle of its home, marking gravitationally the spot where once something extraordinary was happening. When we look at TON 618's light today, we are looking at the ancient past. But in the present right now, wherever TON 618 is sitting in its galaxy, it may have already fallen quiet. The quasar may have faded. The fireworks may be over. All that may be left is the dark, heavy silence and the memory now trapped inside the horizon forever of 10 billion years of falling. I think that is enough for our opening stretch. We have met the object. We have met the people who found it. We have heard the word ultramassive, and we have understood at least roughly what that word is asking us to imagine. And we have begun to sit with two puzzles. The first is why something this heavy should exist so early in the life of the universe. The second is the strange contradiction of a dark thing producing the brightest light we have ever seen, and the even stranger idea that all of the light is from things that are still on their way, and never from anything that has already arrived. Before we move on to the scale of it all, I want you to do one small thing with your mind. I want you to imagine holding the number 66 billion suns in your hand. Not really, of course. You cannot really hold it. The number is too vast for any real handling. But imagine holding the idea of it. Imagine that for every star you have ever seen, every one of the few thousand that are visible from Earth on a clear night, there are millions of stars behind them, and then millions more behind those, and then more and more, and the whole slow cascade of stars out to the furthest galaxies visible to our best telescopes contains somewhere on the order of a few 100 billion trillion stars altogether. 66 billion suns in one place is still only a tiny sliver of that total. The universe is larger than TON 618 by many, many orders of magnitude. And yet, TON 618, concentrated in one gravitational knot, bends space and time around itself in a way that no galaxy, no cluster, no stretch of open cosmos ever does. It is a heavy pocket in a light-expanding universe. It is a place where the rules flex. It is a silence so loud that its gravitational weight alone is enough to pull galactic-scale amounts of matter toward it across distances that a photon would need thousands of years to cross. And we have only just begun to describe it. The next thing we need to understand is how big it is. Not heavy, big. Because heavy and big are not the same thing. And the bigness of TON 618 is in some ways even harder to hold in the mind than the heaviness. When you let your imagination start to walk the distances involved, you quickly find that the walk takes longer than you expected. Longer than a human life. Longer than a human civilization. Longer than the entire age of the Earth. So take a breath. Let the idea of 66 billion suns settle in you like a stone settling into the bottom of a still pond. And when you are ready, we will begin to measure the shadow. Section 2, the scale of the void. Start with your feet on the ground. I want to do this slowly because the only way to really feel the size of TON 618 is to walk outward from something you already know, and to keep walking, and to notice at each step how much larger the idea becomes. If I just told you the number, which is roughly 1,300 times the distance from the Sun to Pluto, the number would slide off your mind the way any very large number does. Numbers that large stop being numbers. They become abstract symbols. They no longer mean what numbers are supposed to mean. So we are going to do it the other way. We are going to start with your feet on the ground, and we are going to walk. Here, where you are right now, the Earth is turning beneath you at roughly 1,000 miles an hour. You cannot feel it, because you and everything around you is turning at the same rate. The ground, the air, the buildings, the trees, the ocean, all of it is turning together. And so, there is no relative motion to feel. The Earth is a sphere about 8,000 miles across. If you walked constantly without stopping at a comfortable 3 miles per hour, it would take you about 110 days to cross the diameter of your own planet. Most people never cross more than a small fraction of that in their whole lives. The Earth alone is already bigger than the human imagination comfortably holds. Now step off the Earth. Put yourself in orbit. Let yourself rise slowly until the curvature of the planet becomes visible, and then further until the continents start to look like fragments on a blue pottery bowl, and then further still until the whole Earth is small enough to be held in your cupped palm, a soft blue marble with wisps of white cloud drifting across its surface. From out here, Earth is beautiful and also suddenly quite small. Keep rising. Let the distance between you and your planet stretch into thousands of miles, then tens of thousands, then hundreds of thousands. At a distance of roughly 240,000 miles, you pass the Moon. Our Moon, our one natural satellite, hanging in the emptiness, pockmarked with craters slowly tumbling in the solar wind. The Moon is not a small object in any absolute sense. It is roughly 2,000 miles across a respectable world in its own right, larger than any asteroid large enough to have its own weak gravity and its own slow geological story. But seen from this distance, the Moon and Earth together look like two spheres hanging in the dark, a big one and a smaller one connected by nothing visible, just the quiet, invisible pulling of gravity. Keep going, pull back further. The Earth and Moon together shrink to a single bright point, and you start to notice other bright points nearby. Mars, Venus, Mercury, the inner planets. They are not arranged neatly the way they look in diagrams. They are scattered around the Sun at their various distances, each on its own slow orbital loop, taking months or years to make a full lap. You keep pulling back, and now the Sun itself begins to shrink from a wide blinding disk into a smaller, still blindingly bright point, and you see finally the shape of our inner solar system. A warm, familiar shape with 8 planets swinging around a central light. The whole orbit of Earth around the Sun, a full year's worth of our planet's travel, is a loop roughly 186 million miles across. Light traveling at 300,000 kilometers a second takes about 16 minutes to cross that loop. So already you see the solar system is not human scale, it is light scale. The distances stop making sense in terms of miles. We have to measure them in terms of how long light takes to cross them. Go out further, past Mars, past the asteroid belt, past Jupiter, a giant gas planet big enough to swallow every other planet in the solar system, put together with its rings of moons, its storms that have been raging for centuries, its faint, subtle band of dust, past Saturn with its famous rings made of trillions of tiny ice chunks, all orbiting in the same plane, like a flat, delicate disk of frost around a pale yellow world. Past Uranus and Neptune, cold, distant blue and blue-green, locked into their long, slow, centuries-long orbits. Out past Neptune at a distance of roughly 3.5 billion miles from the Sun, you reach the orbit of Pluto. Pluto is small. Pluto is in fact no longer considered a full planet, but Pluto's orbit is vast. Light takes more than 5 hours to travel from the Sun to Pluto. A ray of sunlight leaving the surface of the Sun would over the course of an entire afternoon still not have reached Pluto yet. Now pause here, because this roughly is the scale that most people carry around in their heads when they think about the solar system. From the Sun to Pluto, the whole neighborhood of planets, the gas giants, the ice giants, the dwarf planets beyond. This is the space we send our probes into. This is the arena of New Horizons and Voyager and all of the long, slow missions of the last half-century. It takes a fast spacecraft decades to cross this region. In human terms, it is unimaginably large. And now I want you to do something with that scale. I want you to picture the orbit of Pluto as a faint round circle drawn around the Sun, a circle roughly 11 billion miles across. That whole circle, that whole vast ring of space containing the orbits of every planet in our solar system, containing Earth and Moon and Mars and Jupiter and Saturn, containing all of it. I want you to take that circle, that whole picture of our planetary home, and I want you to imagine pushing it gently into the dark, because TON 618 is larger than that circle, much larger. The event horizon of TON 618, the outer edge of the darkness, the boundary beyond which no light can ever return, is estimated to be somewhere between 300 and 1500 times the distance from the Sun to Pluto. The exact size depends on how much the black hole is spinning and on which mass estimate you use. But in round numbers, you could take our whole solar system, every planet, every moon, every comet in its long loop, and place it in the middle of TON 618, and our whole solar system would fit inside with plenty of room to spare. Not just fit, be lost. Be swallowed so completely that it would be like dropping a grain of sand into an ocean and then trying to point out where the grain had gone. Let me give you that number more concretely. The event horizon of TON 618 is estimated to be about 40 times the diameter of Neptune's orbit. That means if you were to stand at the center and look outward, the edge of the darkness, the surface past which nothing returns, would be 40 times farther away than Neptune is from our Sun. It would be so far away that light itself, the fastest thing in the universe, would need something like 3 to 4 days just to travel from the center to the edge. 3 to 4 days. Light. The thing that can cross the distance from the Moon to the Earth in 1¼ seconds. The thing that can reach you from the Sun in 8 minutes. 3 to 4 days just to move from one side of this object to the other. That is the shadow we are talking about. That is what it means to call TON 618, the biggest of its kind. I want to pause and let that sit, because I know the numbers are starting to pile up, and when numbers pile up, the brain starts to blur them together. So let me try another way of saying it. If you could somehow turn TON 618 into a crystal sphere and place it where the Sun is right now, every planet in our solar system out to Neptune and beyond would already be inside that sphere. Earth, Mars, Jupiter, Saturn, all of them. We would not be looking at the black hole from outside. We would be inside it, surrounded by its darkness with no possibility of reaching the edge. The edge by that point would be 30 or 40 times farther from us than the Sun is now. Unreachable, permanently behind us. Even if we turned around and fired off every rocket ever built, we could not escape. And that is just the event horizon. The black hole itself in the old classical picture is concentrated at a single point in the exact center. A singularity, to use the word that physicists sometimes use and sometimes try to avoid. But the event horizon is the edge of its influence, the boundary where the escape velocity equals the speed of light, and inside that boundary, nothing can get out. The event horizon of TON 618 is by any measure one of the largest single features in the known universe. Here is another way to feel it. If you could fly a fast rocket at 1 million miles per hour, 1,000 times faster than the fastest spacecraft humans have ever built straight across the diameter of TON 618, it would take you something like 22 years to cross. 22 years. Most of a human lifetime spent inside a single black hole traveling at 1 million miles an hour, and still, at the end of 22 years, you would only just have reached the other side. At the more ordinary speed of a commercial airliner, about 550 miles an hour, the same crossing would take tens of thousands of years. Crossing one object, not crossing a galaxy, not crossing the distance between stars, crossing one single object. I find it helpful when I am sitting with a number like this to bring in a puzzle piece that feels smaller and more human, something that my mind can still get its hands around. So here is one. Our own Milky Way galaxy is about 100,000 light years across. That is a vast distance. It is vast enough that if you stood at one edge of the galaxy and shone a flashlight across the light from the flashlight, would not reach the other edge until 100,000 years later. If cavemen in the last ice age had turned on such a flashlight, the first photons would still be traveling today and would not arrive for another 90,000 years. The galaxy is huge. Our intuitions break at the size of our galaxy. But TON 618, a single object, is roughly 1,000th the size of the Milky Way. 1,000th of our whole galaxy contained in a single black hole. That ratio is absurd. Normally, when we talk about the objects inside galaxies, we are talking about stars which are trillions of times smaller than the galaxies that contain them. Even the supermassive black holes at the centers of galaxies are by volume a tiny, tiny dot at the center. For a single object to be 1,000th of the size of its entire parent galaxy is by normal galactic standards ridiculous. It is as if in a city the size of Tokyo, a single building were 3 kilometers wide. It would no longer be a building, it would be a neighborhood. And this is an object, not a neighborhood. It is all one gravitational well. Every cubic inch of it is under the pull of a single center of mass. One more comparison, because I think this one is quietly beautiful. There is a small puzzle here that I want you to hold on to. Around TON 618, scientists have detected what is called a Lyman alpha blob, which is a very poetic sounding name for a very specific thing. A Lyman alpha blob is an enormous cloud of hydrogen gas glowing faintly at a particular wavelength of ultraviolet light, surrounding certain very bright, very early objects in the universe. The blob around TON 618 has been estimated at somewhere around 100,000 light years across, which is to say roughly the size of the entire Milky Way galaxy. The object at the center, the quasar itself, is not that big. It is a few light days across, which is tiny by galactic standards. But the hydrogen gas cloud that surrounds it, responding to its radiation glowing faintly in sympathy, is itself the size of a whole galaxy. The black hole at the center is a pinpoint by comparison, even though that pinpoint is larger than our solar system. The web of glowing gas around it could swallow the Milky Way whole. So when you imagine TON 618, imagine 3 nested things. Innermost, a dark heart smaller than the eye can resolve at any telescope we have ever built, where the singularity, whatever a singularity really is, sits. Around that, the event horizon, a shadow so large that our entire solar system would be a dust mote inside it. Around that, the quasar, the shining accretion disk, a few light days across blazing with the light of trillions of suns. And around all of that, draped over it like a soft, patient blanket, the Lyman alpha blob, a galaxy-sized cloud of glowing hydrogen responding to the radiation of everything beneath it. That is the full structure of the shadow. That is the shape of the largest single gravitational object we have ever measured. I want to spend a little more time on this scale because I do not think one walkthrough is enough. The first time you hear a number this large, you do not really absorb it. You nod, you say wow, you move on. But your mind has not really sat with it. It has not really turned the number over. So let me come at it from a different direction. Human beings are built to think about small things. Our whole nervous system evolved to deal with objects that we could see, touch, and react to within a few seconds. We are very good at hand-sized objects. We are quite good at room-sized objects. We are passable at landscape-sized objects. We can, with practice, imagine ocean-sized or country-sized objects, though our imaginations are a little shaky by that point. At planet-sized objects, we start to lose the thread. At solar system-sized objects, we are already relying on analogies and comparisons. And at galaxy-sized objects, we have essentially given up on direct imagination. We just use the numbers and trust them. TON 618 is not a galaxy-sized object. It is smaller than that, but only by a factor of 1,000 or so, which at this scale is barely a factor at all. If you told the ancients that a single object could be 1,000th of a galaxy, they would not have known what you meant by galaxy, of course. But once they understood, they would tell you that such a thing could not be, because nothing is 1,000th of a galaxy. The Earth is not 1,000th of a galaxy. The Sun is not 1,000th of a galaxy, not even close. Our own galaxy contains about 400 billion stars, and the mass of the Sun is about 1/400 billionth of the total stellar mass of the galaxy. Not 1,000th, 1/400 billionth. That is a factor of 100 million smaller than TON 618's relative size to its own galaxy. TON 618 is proportionally 100 million times larger relative to its parent galaxy than our Sun is relative to the Milky Way. The comparison almost breaks when you try to make it. The categories do not quite fit, and yet there it is. A quiet dark dot measured in 2004, reported in a scientific paper, added to the catalogue of known objects, and now a permanent part of our inventory of the universe. Something else about the scale that I want to mention, and then I will let us move on to the next part of the drift. The density of TON 618 is surprisingly low. That sounds strange because we have been talking about something 66 billion suns heavy, and you would think that something that heavy would have to be extraordinarily dense. And in a sense it is. All of that mass is compressed into a region defined by its event horizon. But if you calculate the average density of the object, the mass divided by the volume enclosed by the event horizon, you get a number that is surprisingly less dense than water. Less dense than water. If you could somehow weigh a bathtub-sized portion of TON 618, assuming you could average it out evenly across the whole volume, it would weigh less than a bathtub of water on Earth. This is one of those quiet, counterintuitive facts that breaks people's mental model of black holes. We usually imagine black holes as impossibly dense. And in the small case, for the stellar mass black holes left behind by dying stars, that is basically true. Those black holes have event horizons only a few kilometers across, and the density averaged out is vastly higher than anything in ordinary matter. But as black holes get more massive, the event horizon grows in direct proportion to the mass. Double the mass, double the radius, and volume grows as radius cubed. So volume grows much faster than mass as black holes get bigger. The bigger a black hole gets, the less dense it is on average, to the point where the largest black holes like TON 618 are on a rough per cubic meter basis less dense than air at sea level and much less dense than water. This does not mean, of course, that you could walk through it. You could not. The gravitational field is still overwhelming. The tidal forces at the event horizon of TON 618 are actually quite gentle because the horizon is so large, but once inside, the geometry of space-time itself is bent in a way that makes escape impossible. But it does mean that the popular mental picture of a black hole as a kind of ultra-compressed marble is wrong, at least for the biggest ones. TON 618 is much more like a vast, dark, nearly empty volume defined entirely by the edge past which light cannot return. The mass is there, but it is distributed strangely bent into the shape of the event horizon, lurking somewhere at the center in ways that our physics cannot quite describe. A vast dark volume. That to me is the image to hold in mind. Not a dense point. A vast, sprawling dark through which our solar system could drift for years at the speed of light without ever reaching the other side. And that vast dark is the engine. That vast dark is what powers the quasar. That vast dark is what generates the brightest light in the universe, not by shining itself, but by pulling things in so violently that those things cannot help but shine as they fall. In a few minutes, we will start to understand how that works, because the process by which a dark object generates the brightest light in the universe is one of the more wonderful contradictions in nature. But before we get there, I want to let you breathe for a moment. I want the scale to settle. I want you to feel the difference between the heavy number we met in the first section, 66 billion suns, and the vast number we have been exploring in this section 40 times. The orbit of Neptune 3 light days across. Those are two different kinds of large. One is a weight, the other is a width. And TON 618 has both and has them at a scale that, as far as we can tell, very few other objects in the universe can match. So let it sit. Let the dark sit. Feel the size of it around you. Imagine drifting inside it, weightless, surrounded by kilometers upon light days of quiet, empty space, knowing that nothing you did no speed you could achieve would ever bring you back to the other side of the horizon you just passed through. You would simply be in forever, falling gently, without sound, without edges, toward a center that you could never quite reach in any finite time. And that is the shadow. Not a wall, but a volume. Not a boundary you hit, but a region you enter from which there is no path back out. Now, let us take the dark apart. Let us learn how something with no surface, no light of its own, and no way to signal us from inside can still be the most visible object in the sky from 10 billion light years away. Let us meet the engine. Section 3. The quasar engine. There is something almost funny about black holes in the way that the deepest, strange things in nature are sometimes funny. You can see them because they are invisible. You can find them because they devour everything. The dark makes its presence known through the brightness of whatever is unlucky enough to be falling into it. And if you want to understand how one of the most brilliant lights in the universe can be produced by an object that emits no light of its own, you have to understand that in the neighborhood of something, this heavy matter simply cannot fall quietly. Let me walk you through it slowly. Imagine for a moment a cloud of gas somewhere in the middle of a young galaxy. This cloud is not remarkable by galactic standards. It is a wisp, a few tens of light years across, drifting through the heart of a crowded galactic neighborhood. It is mostly hydrogen with a smaller amount of helium and an even smaller amount of heavier elements. It has a temperature somewhere around a few thousand degrees, which is hot by human standards, but cool for a galaxy. It is moving along its own slow orbit, pulled this way and that by the gravitational fields of nearby stars, by the general pull of the galactic center, and by the mutual attraction of its own parts. In other parts of the galaxy, clouds like this one are slowly collapsing under their own weight, forming new stars, beginning new stellar lives. But this particular cloud is unlucky. It is drifting toward the center. The closer it gets to the center, the more it feels the pull of the object that sits there. At first, the pull is gentle. Over millions of years, it shifts the cloud's path by only a little, but the pull is unrelenting. There is no force pushing outward to balance it, and unlike ordinary gravitational interactions between stars, where the two parties pass each other and go on their separate ways, the cloud is falling towards something from which nothing escapes. There is no passing. There is only approach. As the cloud approaches the central black hole, something begins to happen. The cloud is not falling straight in. Very few things in a galaxy fall straight toward the center. Almost everything has some sideways motion, some orbital angular momentum. So the cloud spirals inward. And as it spirals, it encounters other clouds, other gas, other fragments that are also spiraling inward. They collide, they merge. They begin to form a disk, all orbiting in more or less the same plane, all spiraling slowly toward the center. And as the disk tightens as it gets closer to the black hole, the physics of the situation begins to get more and more extreme. Here is what is happening in that disk. The gas is in orbit, which means it is moving very fast around the center. The orbital speed depends on the distance from the center. Closer in gas moves faster than gas farther out, so the inner edge of the disk is rotating faster than the outer edge. Adjacent rings of gas are sliding past each other at different speeds. This creates friction. The gas rubs against itself. And friction, as you know from any everyday experience, produces heat. But the friction in the accretion disk of a supermassive black hole is not ordinary friction. It is catastrophic titanic friction. The gas is rotating at a significant fraction of the speed of light. The temperatures involved are not the few hundred degrees of a frying pan, nor the few thousand degrees of a star's surface. They are millions, tens of millions, hundreds of millions of degrees. At temperatures like these, the gas does not merely glow, it radiates. It sheds energy at every available wavelength of light, from the low-frequency radio, up through the rainbow of visible colors, and on into ultraviolet and X-rays, and at the hottest parts of the disk into gamma rays. A full spectrum of light pouring outward from the hot, turbulent, rapidly rotating disk. And because the black hole is so massive, the amount of matter that can pile up in this disk is enormous. Galactic-scale amounts of gas funneled by mergers and collisions, and the natural gravity of the region all draining, slowly toward the center, all heating up along the way, all shedding light as they go. The accretion disk of TON 618 is in all likelihood the size of a respectable galactic structure in its own right, measured in hundreds of astronomical units or more. At its inner edges, it is glowing more fiercely than any star. At its outer edges, it fades into a cooler, redder luminescence, still brighter than most individual stars. And the total output of this system, summed across all wavelengths, all directions, all temperatures, comes out to something on the order of 100 trillion suns worth of brightness. 100 trillion suns. That is the light of TON 618. Let me try to give you a feel for that number, because 100 trillion suns is the kind of phrase that sounds impressive but does not necessarily land. Our galaxy, the Milky Way, contains roughly 400 billion stars. If every single one of those stars were as bright as the sun, which they are not, the total brightness of the galaxy would be roughly 400 billion suns. But TON 618, a single quasar, is shining at more than 200 times that. So the quasar is brighter in its peak feeding phase than a couple of hundred entire Milky Ways would be. And all of that light is coming from a region only a few light days across compared to the 100,000 light-year breadth of a galaxy. The brightness per unit volume is simply ridiculous. This is why across 10 billion light-years of distance, we can still see the thing. It is in its blazing moments one of the loudest light sources in the universe. and it is all caused by falling. I want you to hold that for a moment. The light is not produced by the black hole. The black hole is dark. The light is produced by everything that is about to be eaten. The process of falling toward an ultramassive black hole generates so much friction, so much heat, so much radiation, that the fall itself shines more brightly than 100 galaxies. The dark thing at the center is a quiet listener, patient, unmoving, in the sense that matters while all around it the infalling gas screams with light. This is what astronomers call the accretion disk, and it is one of the most beautiful structures in all of nature. Not beautiful because it is calm. It is not calm. It is violent beyond anything most people can easily imagine. It is a place of intense magnetic fields of gas so hot that its atoms are fully stripped of their electrons of shock waves and turbulent eddies and sudden flares. But beautiful because it is so ordered in its overall shape. A flat rotating disk shining with heat spiraling slowly inward, shedding the excess angular momentum that allows any given parcel of gas to spiral in a little closer, a little closer, a little closer still, until at last, at the inner edge of the disk, it reaches the point of no return and vanishes into the dark. There is a small puzzle I want to mention here because it is one of the ongoing mysteries of accretion physics. We do not fully understand exactly how the gas loses enough angular momentum to fall in. In simple models pure, gravity alone would not do it. The gas would just keep orbiting forever the way a planet orbits the sun without falling in. Something has to remove angular momentum from the inner parts of the disk and transfer it outward. For a long time, the leading candidate was magnetic turbulence. Small, tangled, twisting magnetic field lines in the hot, ionized gas carry angular momentum outward and let matter spiral inward. There is good evidence for this, but the full picture is complicated, and parts of it are still being worked out in the computer simulations of astrophysicists around the world today. The accretion disk is both one of the most studied and one of the most mysterious structures in astronomy. Alongside the disk, there is another structure that deserves attention because it is one of the more dramatic things that quasars do. As matter falls in and heats up some of it, not all of it does something surprising. Instead of going all the way in, a portion of the infalling material is flung back out. It is ejected at tremendous speeds in two thin focused beams that emerge from the poles of the accretion disk, one pointing up and one pointing down perpendicular to the plane of rotation. These are called relativistic jets because they are moving at speeds approaching the speed of light. They can be millions of light years long. They can extend out of the host galaxy entirely out into the intergalactic medium, where they dump their enormous energy into huge, faint, puffy lobes of radio-emitting gas that astronomers can detect from across the universe. Not every quasar has prominent jets. Some are radio quiet, meaning their jets are much weaker or absent. TON 618 has jets, though the precise geometry of them is still being studied, and their absolute strength relative to other quasars is somewhat modest. But the fact of jets in general is worth dwelling on. A small fraction of what falls toward the black hole is launched back out at nearly the speed of light in a direction perpendicular to the plane of the disk. Nobody fully understands the launching mechanism. It is thought to involve the black hole's rotation, the magnetic field threading through the inner accretion disk, and a complex process by which energy is extracted from the spinning geometry of space-time itself and used to accelerate particles along the poles. There is a word for this. It is called the Blamford-Znajic process, after the two physicists who first worked out the theory in the 1970s. Parts of the theory have been confirmed by observations. other parts are still being refined. What we know concretely is that quasar jets exist, that they are among the most powerful sustained energy sources in the universe, and that they extend over vast distances, much vaster than the galaxies that contain the black holes producing them. So here is the full picture of what is happening around TON 618 during its active phase. A dark heart at the center, 66 billion suns, heavy, invisible in itself, surrounded by an event horizon that is roughly 3 light days across, beyond which nothing can return. Around the horizon, a brilliant turbulent accretion disk, flat and rotating, rapidly shining with the light of 100 trillion suns, pouring energy out into space in every direction. Along the rotation axis, perhaps 2 thin jets of ultra-fast gas punching their way out through the host galaxy and into intergalactic space. Around all of this, the Lyman Alpha Blob, a galaxy-sized cloud of hydrogen gas glowing faintly in response to the radiation from the central engine. And around that, a young galaxy just starting to assemble its own stars and structures, all while its central region goes through this spectacular and violent phase of supermassive black hole growth. It is an incredible image. A single object can generate an environment like this. A single gravitational knot in the otherwise smooth fabric of the early universe can produce a cascade of physical phenomena, from relativistic jets to galaxy-sized gas clouds, all centered on a tiny dark region, invisible to any light, but bright enough in its effects to be seen from the other side of the observable universe. But the part I want you to hold on to, the part that I find genuinely beautiful, is this. None of this light, none of this radiation, none of the quasar brightness that we see is coming from the black hole itself. The black hole in itself is completely silent. The light is the light of everything it is pulling in. The roar is the roar of falling. If you could, by some magical conceptual subtraction, remove from the scene everything that is currently being devoured, the black hole would disappear from our view entirely. It would go dark. It would become once again what it fundamentally is: a pit, a silence, a weight in the geometry of space with no outward expression of its own. Everything we see from TON 618 is the sound of death, gently put. The light is the last signal of matter that will never ever come back out. When a star wanders too close to an accreting black hole, it can be torn apart in what astronomers call a tidal disruption event. The star does not simply fall in. Before it falls in, the difference in gravitational pull between the near side and the far side of the star becomes so large that the star is ripped apart. The shreds of stellar matter then spread into a long stream, some falling in, some ejected outward, some forming a brief bright accretion flare that lights up the sky for weeks or months before fading away. These events are rare in any individual galaxy, but across the observable universe they are happening all the time, and our telescopes are now beginning to catch them. Some of the flares that have been detected around supermassive black holes in recent years are very likely the deaths of unfortunate stars. For something as big as TON 618, whole star clusters, whole small galaxies can be pulled in over time. The black hole grows by eating. Every photon of quasar light that reaches us is the signature of matter that is, in a sense, in the act of saying goodbye, not screaming in pain. The matter itself is just atoms, just gas, just plasma, with no awareness of its situation. But if you wanted to imagine it poetically, you could. You could say that every flicker of quasar light is the last visible signal of something that a short while later is gone from our universe forever. And TON 618 has been doing this, emitting such signals for far longer than our planet has existed. The timescales here are worth thinking about. Quasars do not shine forever. As the available gas in the central region of a galaxy is consumed, the quasar fades. As the host galaxy stops merging with new partners, the supply of fresh fuel slows. Eventually, the central black hole runs out of nearby food and goes quiet. It is still there, still 66 billion suns of dark mass, but it is no longer accreting rapidly, no longer generating the intense radiation of an active quasar. It becomes a quiescent supermassive black hole like the one in our own Milky Way center, which is currently not actively feeding in any dramatic way. Every now and then, a cloud of gas or a star wanders close enough to stir things briefly. There can be flare-ups, brief quasar-like episodes, tidal disruption events. But the main stable state of most supermassive black holes most of the time is quiet. Waiting. So TON 618, as we see it, is in the middle of its feast. The light we see is 10.5 billion years old. That means in the present-day universe, TON 618 has had 10.5 billion years to continue its story. It may still be actively accreting today. Some ultramassive black holes are still quasars in the present, or it may have gone quiet. Or it may have undergone further mergers with other supermassive black holes as its host galaxy merged with other galaxies growing even larger, or being joined by a companion, or being pulled apart by extreme gravitational dynamics. We do not fully understand. We cannot see the present-day version of TON 618. Its light from today has not yet arrived, and will not arrive for another 10 billion years, by which time our sun will have long since died. We will never, in any practical sense, know what TON 618 is doing now in the frame of our own clocks. We can only see what it was doing in the youth of the universe, sending its 10 billion-year-old postcard toward us across the void. A small puzzle here before we move on. The accretion disk of TON 618 is so bright that when astronomers first estimated its brightness by brute measurement, they had to double-check whether anything was wrong with the instruments. Some calculations suggested that the total luminosity exceeded what is known as the Eddington limit, the theoretical maximum brightness at which radiation pressure would start to blow the infalling gas outward and halt further accretion. If TON 618 is really shining brighter than its Eddington limit, that suggests one of several possibilities. It could be that the geometry of the accretion flow allows some of the radiation to escape without pushing out the gas, perhaps because the gas is falling in from certain directions and the radiation is escaping in others. It could be that our mass estimate for the black hole is too low, and the Eddington limit is therefore higher than we think. Or it could be that the brightness estimate itself is inflated by some combination of effects we do not fully account for. The tension between the measured brightness and the Eddington limit is one of those ongoing puzzles in the TON 618 literature. It is a place where the standard picture of accreting supermassive black holes is being tested and in some details perhaps overturned. I love these little puzzles because they remind me that even the most dramatic objects in the universe are not completely understood. We have a rough picture, we have the big outlines, but the fine details, the exact numbers, the precise mechanisms by which something as extreme as TON 618 does what it does are still being worked out. Every few years new papers come out refining the measurements, tightening the theoretical models, bringing the picture a little more into focus. And every few years new puzzles pop up, suggesting that there are still aspects of quasar physics that our current theories do not quite capture. It is tempting to think of science as a finished thing. It is not. It is a conversation still in progress, full of people patiently turning over the same stones again and again, sometimes finding something new underneath. Ton 618 is one of those stones. It has been sitting in our catalogue of the universe for decades. But every new look at it reveals something slightly new. The field is not done with this object yet. One more image before we leave the engine behind and start talking about time. Picture, if you can, the accretion disk of Ton 618, seen from above. A vast flat disk rotating with different regions moving at different speeds. The very innermost edge is closer to the event horizon, closer to the center, moving at a fraction of the speed of light. As it rotates, the light coming from the side that is rotating toward us is shifted slightly toward the blue because of the Doppler effect, which tells us that sources moving toward us appear bluer. The light from the side rotating away from us is shifted toward the red. This difference between the blue shifted side and the red shifted side of the inner disk is actually measurable in some systems. It is in fact part of how astronomers estimate the black hole's mass and the geometry of the accretion flow. The disk seen from a distance is not just a bright blob. It has a structure. It has a tilted axis. It has a blue side and a red side. It has magnetic fields threading through it in complicated, ever-changing patterns. It is a living, breathing, energetic structure in its own violent way, feeding into the stillness at its center. There is a puzzle worth pausing on here, which is the efficiency of this whole process. Accretion onto a spinning black hole is, in terms of pure energetic accounting, one of the most efficient known processes in the universe for converting mass into light. A nuclear fusion reaction of the sort that powers our sun converts about 0.7% of the mass of the hydrogen involved into usable energy. That is already impressive. Nuclear fusion is why stars shine for billions of years. But accretion onto a rapidly rotating black hole can, in theory, release up to about 40% of the infalling mass as radiation. 40%. That is more than 50 times the efficiency of stellar fusion. It is why, even though the amount of matter falling into Ton 618 in any given year is only a small fraction of its total mass, the light produced is so extraordinary. Very little matter, when it falls far enough down into a gravitational well this deep, produces a tremendous amount of light on its way down. The infalling gas is not burning in the nuclear sense. It is simply giving up its gravitational potential energy, and that energy, in the extreme conditions of the inner accretion disk, comes out mostly as radiation. The black hole, in this sense, is a kind of cosmic alchemist. It turns mass into light, not by any chemical or nuclear process, but by the pure geometry of its gravity, and at its center, always the dark. I think that is enough about the engine. I have taken us slowly through the physics, and I hope you can now hold in your mind the picture of Ton 618 as a luminous disk around a dark core. Not a flame, not a star, not a burning thing in any ordinary sense. An object whose central feature is its absence. An object whose light is entirely borrowed from the matter that is about to disappear into it. An object whose brightness, incredibly, is in direct proportion to how much it is eating. Now we are going to step away from the engine and turn to something different. Because in order to see Ton 618 at all, the light had to travel a very, very long way to reach us. And when we talk about that journey, we are not just talking about distance, we are talking about time, about the depth of time, about how looking at Ton 618 is looking into the past more directly than almost any other act human beings are capable of. So let us turn off the engine for a bit in our minds and let the light drift. Let us think about what 10 billion years of travel means, not in miles, not in light years, but in the slow, slow turning of cosmic history. Let us think about what Earth looked like when this light first set out. Let us think about who we are in the chain of events this photon has been traveling through to be the ones who finally catch it. Time in this case is going to be both strange and beautiful. Time is going to be almost everything. Section 4. The Time Traveler's Perspective. When you see a star in the sky tonight, you are not seeing it as it is. You are seeing it as it was some years ago, whenever the light you are receiving happened to leave its surface. For the nearest stars, that delay is only a few years. The light from Alpha Centauri, our closest stellar neighbor, takes a little over 4 years to reach us. When you look at Alpha Centauri tonight, you are seeing the star as it was 4 years ago. For the more distant stars visible to your naked eye, the delay can be a few hundred or a few thousand years. The light of Betelgeuse takes around 500 years to reach us. So if you are watching Betelgeuse tonight, you are seeing it as it was when the Renaissance painters were still at work in Florence. Every act of looking up at the night sky in this sense is an act of looking into the past. This is a familiar idea. Most people who have spent any time with astronomy have heard it before. But what makes TON 618 special, what makes it worth pausing on, is that the depth of time involved is so much greater than the ordinary case. The light of TON 618 did not leave 4 years ago. It did not leave 500 years ago. It did not leave at the dawn of human civilization. It left before the dawn of almost everything we know. 10.5 billion years. That is the number. 10.5 billion years ago, the photons we are now detecting began their long journey. To put that in the context of cosmic history, the universe itself, according to our best measurements, is about 13.8 billion years old. That means when this light left TON 618, the universe was already mature enough to contain fully formed galaxies and ultramassive black holes, but it was still in its first third, its early stretch, its morning. Only about 3 billion years had passed since the Big Bang. Our own solar system would not exist for another 6 billion years. Life on Earth eventually would be another 7 or 8 billion years in the future. So let us walk through what was and what was not when this light began its journey. Begin here. Your own body, your own cells, the atoms that make you up, did not exist yet in any assembled form. Some of the atoms, the hydrogen atoms in particular, did exist. Most of the hydrogen in your body and most of the hydrogen in the universe dates from the first few minutes after the Big Bang. But the heavier elements, the ones that make up most of the interesting parts of a human body, the carbon, the nitrogen, the oxygen, the calcium in your bones, the iron in your blood, were still being assembled inside stars and would be for billions of years. When the light of TON 618 began its journey, only a few generations of stars had lived and died. The heavier elements were still being cooked into existence slowly over generations of supernovae in galaxies that were themselves still young. There was no Earth. There was not even yet the cloud of gas from which the Earth would eventually form. That cloud would coalesce out of the debris of earlier stellar generations over the next 6 billion years. There was no sun, the star from which Earth would one day draw its warmth. The 5 billion year old main sequence star we call the Sun had not yet ignited. The dust and gas that would one day form it was still drifting, waiting, scattered somewhere in the slow arms of what would eventually become the Milky Way. The Milky Way itself at that point was a much smaller, still assembling galaxy. It was swallowing smaller companions, merging with other proto-galaxies, gradually building up to the shape and size it has today. If you had been there then standing on some imaginary platform in the early universe, you would not have recognized the Milky Way as our home. It was something else still becoming. There was no moon of any kind hanging over our planet because there was no planet to have a moon. There were no oceans. There was no atmosphere. There were no continents. There were no dinosaurs, obviously, but more than that, there were no bacteria, no single-celled life of any kind. The machinery of biology had not yet been invented, and the planet on which biology would one day emerge had not yet been assembled. All of the drama that we call Earth history, all of the slow accretion of a planet out of dust, all of the eons of cooling and oceans forming, and the first organic molecules, and the first cells, and the long, slow Cambrian explosion, and the rise and fall of dinosaurs, and the emergence of mammals, and the evolution of primates, and the eventual appearance of humans, every single bit of that compressed into a single chapter of cosmic history was still in the future. That is the shape of 10.5 billion years ago. The light of Ton 618 leaves, its source travels across expanding space, and during that travel, all of Earth's history from planet formation to your own life occurs. The photon does not care. It keeps traveling. It is in the middle of a journey that is longer than any journey we can easily comprehend, and as the journey passes, whole worlds are born, and whole species rise and fall on a tiny blue planet that the photon will eventually reach. The photon did not aim at Earth. It was not sent toward us. Earth was not even here yet. But by some quite unremarkable coincidence, the line of travel that the photon happened to take out from the hot surroundings of Ton 618's accretion disk ended up eventually passing through a point in space where billions of years later our planet would form and a civilization would build a telescope. The photon arrives. A sensor notices it. A data point is added to a spreadsheet. An article is eventually published. And now you drifting towards sleep in the middle of a calm universe are being told the story. What was happening on Earth while that light traveled? Nothing. For the first 6 billion years or so of the photon's journey, Earth did not exist. The solar system was slowly assembling somewhere in the outer regions of the young Milky Way, as the galaxy itself was still being built. The photon traveled through expanding space past other young quasars, past galaxy clusters that were themselves still forming through the cosmic web of filaments and voids that makes up the larger scale structure of the universe. The universe was steadily cooling, steadily stretching, steadily turning from the dense, hot, young state into the diffuse, cool, middle-aged state it occupies now. And the photon rode through all of that uninterrupted because the space it was crossing was mostly empty at large scales, and a photon in empty space simply continues. Then, about 4.5 billion years ago, our sun ignited. A cloud of gas enriched with the heavier elements from previous stellar generations collapsed under its own gravity, formed a hot core, and began fusing hydrogen into helium in its very center. Around the new star, a disk of leftover material settled into a flat plane, and slowly, over tens of millions of years, dust grains stuck to other dust grains to form pebbles, and pebbles collided to form rocks, and rocks merged to form the cores of planets, and Earth eventually was born. All while the photon kept traveling, Earth cooled, oceans formed. Life began in some still mysterious process, perhaps at deep-sea hydrothermal vents, perhaps in shallow pools, perhaps in both, perhaps in many places at once. Single-celled life slowly gave rise to more complex single-celled life, and eventually to multicellular life. For billions of years, life remained microscopic and subtle. Then about 500 million years ago, complex animal life exploded across the seafloor in what is called the Cambrian explosion, and the world was transformed. Over the following 500 million years, life diversified into every niche the planet had to offer. Fish, amphibians, reptiles, dinosaurs, mammals, plants on land, forests, swamps, deserts, ice caps, tropical oceans. A whole planet busy with biology, and all the while the photon from Ton 618 kept traveling. Nobody noticed it. Nobody could have noticed it because nobody had eyes yet that could detect such faint distant light, and nobody had telescopes, and nobody even had the concept of a telescope because nobody did not yet exist in any relevant sense. Dinosaurs died out, mammals expanded, primates evolved. Our ancestors walked on 2 feet and began making stone tools. The photon kept traveling. A few 100,000 years ago, our species appeared. Homo sapiens. Anatomically modern humans roaming the African savanna building small tools, making fire, burying their dead. For most of that time, humans lived in small bands without agriculture, without cities, without writing. The photon kept traveling. 10,000 years ago, agriculture began. Cities followed. Writing, metallurgy, trade routes, empires. The whole sweep of human history that we study in school, from the ancient Near East to classical antiquity, to the medieval world, to the Renaissance, to the Industrial Revolution, all of it unfolded in the last few thousand years. The photon kept traveling. A few hundred years ago, humans began to systematically look at the sky with instruments. Galileo pointed a telescope at Jupiter and saw the moons. Kepler worked out the laws of planetary motion. Newton realized that the same gravity that pulls an apple to the ground also holds the planets in their orbits. Over the next 3 centuries, telescopes got bigger, instruments got better, and the universe slowly revealed more of itself. The photon kept traveling. A little over a century ago, Einstein worked out the general theory of relativity, which predicted the existence of black holes as a mathematical consequence of how gravity curves space-time. For a long time, nobody was sure whether real black holes existed or whether they were merely a curiosity of the math. The photon kept traveling. About 60 years ago, quasars were first identified as a new class of bright distant object, and the suggestion that they were powered by supermassive black holes began to take hold. The photon kept traveling. The photon by this point was getting close. Only a few years of its journey remained. In 2004, Hiron Spinrad and his team made the measurement we have been talking about. The photon arrived. The journey was over. The number came out of the instrument. 66 billion suns. That is what was happening on Earth, while the light of Ton 618 traveled to us. Or more accurately, that is what was happening on Earth for the last third of the journey. The first 2/3 happened before there was an Earth at all. I find this almost unbearable in a good way. There is a kind of vertigo that comes from realizing that the light you are receiving now is older than your home planet. You are not looking at the universe. You are looking into the universe's own memory. You are receiving a signal that is older than almost everything you think of as real. The mountains you have seen, the oceans you have swum in the bodies of every person you love, the atoms in your own fingers, all of them were assembled, arranged, and brought into their current form long after this photon began its travel. The photon is older than the ground you walk on, and there is nothing unusual about this in cosmic terms. Every photon we receive from every distant object in the universe carries a similar kind of depth. When we look at the most distant galaxies known, our telescopes receive light that is more than 13 billion years old, light that began its journey when the universe itself was barely any age at all. Ton 618's light at 10.5 billion years old is not even the oldest light we see. It is just one of the older objects in our catalogues, and one of the most massive. But TON 618 is special for a different reason. It is not just far away, it is spectacularly massive. It is one of the largest single things we have ever been able to measure. And so, when we receive the 10 billion-year-old light of TON 618, we are receiving a signal from a monster that was already at that early point in cosmic history fully grown. The universe had only been running for 3 billion years, and there it was, a black hole weighing 66 billion suns, already feeding voraciously, already the brightest thing in its neighborhood, already a fully developed cosmic heavyweight. This brings us back to one of the puzzles I mentioned at the beginning. How did it get so big so fast? If we assume a black hole starts as a small seed and grows by accretion running full steam ahead at the Eddington limit the whole time, it still takes a long time to get from a small seed to 66 billion suns. There are models that suggest some early black hole seeds might have been much larger than stellar mass remnants. Direct collapse scenarios in which enormous clouds of primordial gas collapse directly into black holes of tens of thousands of solar masses have been proposed as the origin of the first supermassive seeds. With a running start like that, and with a rich feeding environment over the first 3 billion years, a black hole might plausibly reach the TON 618 scale by the redshift at which we see it. Well, or there might be exotic scenarios. Some theorists have proposed primordial black holes formed in the very first moments of the Big Bang as possible seeds for later giants. Others have explored whether ultra-efficient accretion, in which gas falls in at rates well above the Eddington limit, thanks to unusual geometries or beamed radiation escapes, might allow black holes to grow much faster than the standard picture allows. Still others wonder whether multiple smaller supermassive black holes formed in separate protogalaxies could merge rapidly during the chaotic galactic mergers of the early universe, stacking their masses on top of each other. The true answer is likely some combination of all of these factors. TON 618, in other words, is a window not just into cosmic distance, but into cosmic early history. It tells us that whatever the mechanism, the universe was able to build enormous gravitational giants surprisingly fast. The standard story of slow, steady growth cannot easily explain what we see. Something about the early universe was unusually generous to the largest black holes. Something let them grow rapidly to scales that even now are astonishing. And when you sit with that, another layer of the drift opens up. We are not just looking at a large object, we are looking at a piece of evidence that the early universe was stranger and more productive of monsters than our simple models would suggest. The brightness we see, the mass we have measured, the spectral lines we have passed, all of it is telling us something not just about one object, but about the conditions in which such an object could arise. The early universe had rich gas supplies, rapid galactic mergers, and mechanisms for black hole growth that we are still working to understand. TON 618 is one of the clearest signs that whatever was going on back then, it was enough to produce gravity wells that even today sit at the edge of what our physics says is possible. I want to add one more piece of the time traveler perspective, because I think it rounds out this section nicely. When astronomers talk about the distance to TON 618, they often use the phrase light travel time, which is the time the light has spent on its way to us. That is 10.5 billion years. But because the universe is expanding the current distance to TON 618, if we could somehow freeze time and measure, it is much greater than 10.5 billion light years. The space between us has been stretching the whole time the photon has been traveling. By the time the photon arrives, the source has been carried by the expansion of space to a distance much larger than where it was when the photon left. The estimated co-moving distance to TON 618, roughly speaking the distance it is from us now taking into account the expansion of space, is something like 18 billion light-years. That is farther than the age of the universe in light-years, which sounds paradoxical, until you realize that the expansion of space is carrying things away from us faster than light can travel across the stretching region. No object is moving faster than light through its local region of space, but the space itself is getting bigger. And so the distance between us and TON 618 has grown steadily over the last 10.5 billion years, from somewhere around a few billion light years to something like 18 billion light years today. That is a strange thing to think about. When you look at TON 618, you are seeing it where it used to be, where it was at the moment the light left. But where it is now, in any sensible meaning of those words, is somewhere else entirely, much further. So far, in fact, that we will never receive light from its present state. The expansion of the universe will carry it beyond our observational reach before any signal from today could ever travel back to us. TON 618 is, in the modern cosmological sense, almost past the horizon of the observable universe, at least as far as any future light from it is concerned. We can only see its past. Its present is unreachable. Its future is inaccessible. We have a 10 billion year old photograph and nothing else, forever. There is a small puzzle woven into this that I want to mention, because it connects back to the Lyman alpha blob I mentioned earlier. When we look at TON 618, we see the quasar light the point source glare of the central engine. But with more careful observations, astronomers have also mapped the enormous cloud of hydrogen gas surrounding it, glowing faintly at the specific ultraviolet wavelength that excited hydrogen emits. That cloud is roughly 100,000 light-years across. The light from the near side of that cloud is reaching us about 100,000 years earlier than the light from the far side. 100,000 years in cosmic terms is not very much, but it means that within a single image of the TON 618 system, we are seeing a tiny smear of time, not a single instant. The near parts of the glowing blob are, from our perspective, 100,000 years younger than the far parts. The image is layered the way a long exposure photograph is layered, with moments from different times all overlapping into a single visible impression. This is a subtle point, but it speaks to the nature of looking across cosmic distances. Nothing we see is really at a single moment. Every photograph of a distant object is in some sense a collage of different moments, drawn from different parts of the object, each arriving after a different travel time. For TON 618, the accretion disk is small enough that the time smear across it is only days or weeks, essentially nothing on cosmic scales. But for the Lyman alpha blob, the smear is about 100,000 years. And for the larger scale features of distant cosmic structures, light travel times can cause smears of millions of years within a single observational field. The universe we see is not a snapshot. It is a weave. It is many moments braided together, each one arriving on its own schedule, each one contributing a different thread to the image we eventually build. There is something calming about that, even though it should feel sad. We live in a universe where the scales of time and space are so vast that certain things simply cannot be reached. Certain knowledge simply cannot be obtained. There is no engine we could build, no signal we could send, no clever trick of physics that could bring us up to date on TON 618. All we have is the photograph. And the photograph tells us something incredible. And we accept that, and we hold it, and we move on. That, in a sense, is what science often is. Accepting what the universe is willing to show us. not demanding more than the universe can give, taking the 10-billion-year-old photograph for what it is, and learning as much as we can from it, and knowing that there will always be parts of the cosmos that stay permanently just out of reach. So here we sit, a small warm species on a small cool planet, around a small yellow star, in a small arm of a medium-sized galaxy holding a photograph from the early universe. The photograph shows a monster, 66 billion suns. Dark at the center, blazing around the edges, drifting its quasar light toward a place where 10.5 billion years later, we would build eyes good enough to catch it. The photograph is what we have. The monster itself is out of reach, and somewhere deep in the object itself, deep past the horizon, past the bright disk and the jets and the blob of glowing hydrogen, the physics of space and time get strange in ways that Einstein first worked out on paper a little over a century ago. We can speak about those conditions in a limited way. The mathematics allows us to describe them up to a point. Beyond that point, our theories fail. The center of a black hole is a place where our current physics breaks down. And that is where we are going next. So let us move inward. Let us leave the quiet drift of photons behind, and let us approach the rules themselves. Let us walk carefully into the place where space and time stop behaving the way we are used to them behaving. Section 5. The limits of physics. There is a boundary around every black hole that is not a physical surface in any ordinary sense. You could not reach out and touch it. It has no texture. It does not glow, does not vibrate, does not mark itself in any way that a passing observer would notice from the outside. And yet, it is in some sense the most absolute boundary in all of physics. Once you cross it, you cannot return. The mathematics that describe it are clean and elegant. The implications of crossing it are strange enough that they have occupied the best minds in theoretical physics for 100 years. The boundary is called the event horizon. The mathematical radius of the event horizon is called the Schwarzschild radius, after Karl Schwarzschild, a German physicist who remarkably worked out the exact solution to Einstein's equations for a spherical non-rotating mass while he was serving on the Russian front in World War I. Einstein had published the general theory of relativity in late 1915. Schwarzschild, a sick man in a war zone, read the paper and produced within months the first exact solution to the equations. He mailed it to Einstein. He died shortly afterward of an illness contracted at the front. His solution describes the geometry of space-time around any spherical mass, and it has buried inside it the mathematical structure of a black hole. At the time, nobody was quite sure whether this structure corresponded to something physically real. Einstein himself was skeptical for decades. It took generations of further work through the middle of the 20th century before black holes came to be widely accepted as genuine astrophysical objects. The Schwarzschild radius is easy to calculate given the mass of the object. It is proportional to the mass through a simple formula. For our Sun, the Schwarzschild radius is about 3 kilometers. For the Earth, if you compress the Earth down to a black hole, the Schwarzschild radius would be about 9 millimeters, roughly the size of a small marble. The whole Earth crushed down to a ball the size of a cranberry. For Ton 618, with 66 billion solar masses, the Schwarzschild radius is extraordinary. It is, as we discussed before, on the order of hundreds of astronomical units, which is to say many times the size of our solar system out to Pluto. 3 to 4 light days across. That is the mathematical boundary past which, if anything crosses, nothing can return. What exactly happens when something crosses the event horizon is one of the most discussed questions in theoretical physics. The answer depends partly on whose physics you trust and how much you believe in the mathematical extensions of our theories beyond the places we can test them. But the rough picture within classical general relativity is strange enough on its own. As you approach a non-rotating black hole from outside the geometry of space-time, begins to curve more and more sharply. Nothing dramatic is happening at first. The curvature is mild. But as you get close to the event horizon, the geometry twists in an increasingly extreme way. From the perspective of an observer far from the black hole watching you fall in, you appear to slow down. Clocks in your spaceship tick more slowly as measured by the distant observer. Your light becomes redder and redder because as photons struggle to climb out of the gravitational well around the black hole, they lose energy and their wavelengths stretch. Your image on the distant observer's screen gradually dims and reddens and slows. In the limit, you never quite reach the event horizon from the distant observer's point of view. You asymptotically approach it, your image fading and reddening forever without ever quite crossing. From your own perspective, however, things are very different. You do not notice yourself slowing down. Your clock continues to tick at its normal rate in your own frame of reference. You fall steadily toward the horizon. There is no wall. There is no jolt. There is no alarm that rings when you cross the mathematical boundary. You simply pass through it and continue falling. For an observer falling into a very large black hole like TON 6 and 18, the event horizon is an unremarkable patch of space. The curvature at the horizon is actually quite gentle because the horizon is so large. Tidal forces, the differences in gravitational pull between your feet and your head are mild. You could pass through the horizon without physically noticing anything, and then from the moment you cross, something changes. Nothing visible in the first instant, but the structure of space-time has shifted. Inside the event horizon, the mathematics of Schwarzschild's solution reveals something extraordinary. The radial direction, the direction pointing inward toward the center, takes on the character that time has on the outside, and the time direction takes on the character of a spatial direction. This is a weird statement. It deserves to be unpacked slowly, because it is strange in a way that most people who have not studied general relativity have never heard about. But it is, as far as we can tell, really what the equations are saying. On the outside of a black hole, the direction we call time is different from the three directions we call space. You can move freely through space. You can walk forward, backward, left, right, up, down. But through time, you only move in one direction, forward, always forward at a rate of 1 second per second in some local frame. You cannot stop the flow of time. You cannot reverse it. You cannot choose not to go through it. Time, in that sense, is a one-way street. Inside a black hole, according to the classical mathematics, something like that same rule applies, but to space. The radial direction pointing toward the center becomes, in a certain technical sense, time-like. You cannot avoid moving toward the center. You cannot turn around. You cannot stay where you are. Moving toward the center of the black hole once you are inside is as inescapable as moving forward in time is from your ordinary experience. No matter what engine you fire, no matter what maneuver you try, you will reach the center. You have no choice. The direction of inward has become the direction of future. This is a counterintuitive claim, but it is what the equations say. It is part of why nothing can escape from inside a black hole. It is not that light cannot run fast enough outward. It is that inside the horizon outward is no longer a direction in space in the way it was on the outside. It has become something more like backward in time. You cannot go back in time, not in this framework. and so you cannot go outward from inside the black hole. The rules that forbid you to reverse the direction of time's flow in the usual case also forbid you to leave the black hole in the case where you are, inside it. The two things are in this mathematical sense the same prohibition. This is what physicists sometimes mean when they say that the interior of a black hole is a place where the rules break. The rules that usually govern space and time get rearranged. The interior is not just a different space. It is a space where some of the basic distinctions we are used to have dissolved. At the center of the black hole in the classical picture is what is called a singularity. This is a place where the equations themselves break down. The curvature of space-time becomes infinite. Density, if we can even use the word, becomes infinite. Tidal forces become infinite. The mathematics just stops producing meaningful answers. There is nothing in the current framework that tells us what is really happening at the singularity because the framework itself does not apply there. Physicists generally assume that the singularity is not real in the literal sense, but is rather an artifact of the fact that we are using a theory, general relativity, which is known to be incomplete. At the extreme conditions near the singularity, quantum mechanics should come into play, and we do not yet have a complete theory that combines gravity and quantum mechanics in a fully successful way. Various candidate theories, quantum gravity string theory loop, quantum gravity and so on, offer partial pictures of what the singularity might really be. Some suggest it is not a point, but a small, perhaps Planck-scale structure, where the smooth geometry of space-time is replaced by something discrete and grainy. Others suggest more exotic possibilities, like that black holes open into other regions of space-time, or that they contain tiny universes of their own, or that they terminate in some kind of quantum bounce that prevents the singularity from ever actually forming. For TON 6/18, with its 66 billion solar masses, the singularity, whatever it really is embedded inside a vast interior, roughly the size of our solar system, or larger. The journey from the event horizon to the singularity for an infalling observer takes some noticeable amount of proper time, though exactly how much depends on the details of the observer's trajectory and the black hole's spin. In the classical picture for a non-rotating black hole, an observer falling freely from just inside the horizon to the central singularity would experience it all in a surprisingly short time, on the order of hours to days for TON 618 size. Hours to days of quiet falling through a region where space and time are rearranged with no way to turn back, ending at a place where physics as we know it gives up. That is the classical picture. It is strange and beautiful and deeply unsettling all at once. There is another feature worth mentioning. Most real astrophysical black holes are rotating. The Schwarzschild solution assumed no rotation for mathematical simplicity, but real black holes formed from the collapse of rotating stars or grown by accreting rotating material pretty much always have angular momentum. The equations for rotating black holes worked out by Roy Kerr in 1963 describe a richer and more complicated geometry. A rotating black hole has two horizons, not one. It has a region called the ergosphere just outside the outer horizon, where space-time itself is dragged around with the rotation so that no object can stand still relative to a distant observer. Inside the ergosphere, even though you are not yet past the event horizon, you are forced to rotate with the black hole. You can still escape. You can still fire an engine and fly away from the ergosphere. But you cannot stop rotating as long as you are inside it. Space-time itself is spinning, and you are along for the ride. Inside a rotating black hole, the interior geometry is even stranger. The singularity in Kerr's solution is not a point, but a ring. And the interior structure contains regions where mathematically, one can imagine paths that would lead to places elsewhere in space-time. Most physicists suspect that these exotic features of the mathematical solution are not realized in real physical black holes because they require idealized conditions that do not hold in practice, but the mathematics is there suggesting that rotating black holes are structurally even weirder than non-rotating ones. TON 618 is very likely rotating. Most supermassive black holes are. How fast is TON 618 spinning? It is hard to say from the data we have. The spin affects the brightness and structure of the accretion disk in measurable ways, and from the properties of TON 618 spectrum, there are some constraints but no definitive answer. It may be rotating at a significant fraction of the maximum possible rate allowed by general relativity, or it may be rotating relatively slowly. Either way, its event horizon is vast, its interior is vaster, and its center, whatever it really is beyond anything our current theories can fully describe. There is another layer to all of this that I find genuinely moving, and I want to try to describe it. The event horizon is often described as a boundary, a surface, a point of no return. But from the perspective of the black hole itself, or rather, from the perspective of the mathematical geometry of the black hole's interior, the event horizon is not really a location. It is more like a moment in time. Once you are inside the horizon is not behind you in space. It is behind you in time. It is in your past, not in a direction you could point to. You cannot look back at it the way you would look back at a door you had just walked through. You can only remember having been on the other side of it. The crossing was an event, not a location. And moving back to the other side would require moving backward in time, which, as we noted, is not something permitted by the underlying physics. Let me let that sit for a moment, because there is something almost poetic in it. The event horizon is not a wall you have crossed. It is a yesterday. It is a moment in your past that you can no longer reach, the way you can no longer reach the sunrise you saw this morning, or the laugh you shared with someone yesterday afternoon, or the first words of any conversation you have ever had. You cannot go back. You can only remember. And for someone inside a black hole, outside the black hole, becomes a memory, not a destination. The world outside the horizon is not a place they cannot reach. It is a place they used to be. This is the deepest meaning, perhaps, of the phrase point of no return. The return would require you to move against the direction of time, and nothing in physics allows that. There is another feature of this time bending that I want to describe because I think it is one of the strangest consequences of general relativity when applied to something the size of TON 618. Gravitational time dilation, the slowing of clocks near massive objects, is a real measured confirmed phenomenon. Near the Earth it is small. Clocks at sea level run very slightly slower than clocks on top of a mountain, and this has been measured with extremely precise atomic clocks. Near the Sun, the effect is larger but still quite modest. Near a supermassive black hole like TON 618, the effect can become enormous. If you could hover very close to the event horizon a few kilometers above it, your clock, as measured by a distant observer, would be running at a tiny fraction of its normal speed. A day on your wristwatch might correspond to a year or 1,000 years for someone far away. If you lingered there long enough by your own reckoning and then flew back out to rejoin the universe, you would find that billions of years had passed while you were gone. The universe you came back to would be unrecognizable. I find this one of the most poetic consequences of general relativity. Deep gravitational wells are in a very real sense regions of slow time. reality itself ticks differently in different places. What is 8 billion years from the outside can be only a few hours from very close to a big black hole. This is not science fiction. This is what the equations predict and what on smaller scales we have directly measured. For TON 618, the effect becomes so extreme near the horizon that it stops being a curiosity and starts being a genuinely strange feature of the geometry. Time itself stretches near a monster like this in ways that change the meaning of duration. None of this, I should say, is something any real observer would ever experience. Nobody is going to fly to TON 618. Nobody is going to hover near its event horizon and come back changed. The object is too far away, too dangerous, too fundamentally inaccessible. But the physics is real. The time stretching happens. If you could somehow be there, it would happen to you. And knowing that this is a real consequence of the geometry of space-time, that reality itself is flexible in this way, is part of what makes sitting with a thing like TON 618 feel so strange. You are sitting with an object around which time itself bends differently than it does here. You are at a deep level aware of the fact that the universe's flow is not uniform. It varies, it slows, it adjusts itself to the presence of mass. I want to mention one more classical feature because it is the kind of thing that people sometimes find beautiful. It is possible in principle to send a message into a black hole. You can aim a laser at it, or throw in a probe with a transmitter, or drop something in. As long as you stay outside the event horizon yourself, you can keep sending information inward. But no message, no signal, no returning probe, no reflected light can ever come back out. Information in the classical picture falls in and is lost. From the outside, a black hole is in principle a one-way channel. It is a place where you can speak, but never hear. This, incidentally, is part of what caused the famous information paradox that Stephen Hawking spent much of his later career working on. Hawking showed in the 1970s that black holes should actually emit a very faint, very slow trickle of radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, is blackbody radiation at a very low temperature, corresponding to a temperature much colder than the cosmic microwave background for any astrophysical black hole. For TON 618, the Hawking temperature is so low, so nearly zero, that detecting it directly would be hopeless. But its existence in principle raises a puzzle. If a black hole slowly radiates away its mass as Hawking radiation, then eventually, over unimaginably long timescales, the black hole would evaporate completely. And what happens to all the information that fell in during its lifetime? The radiation that comes out appears, at least in Hawking's original calculation, to be essentially featureless. It does not seem to carry the specific information of what fell in. That would mean information is destroyed when a black hole evaporates, which is a very uncomfortable conclusion for physics, because the equations of quantum mechanics require that information be preserved. For decades, physicists have debated what happens to information that falls into a black hole. Some argue that it is somehow encoded on the event horizon, smeared out on a surface, and eventually released in the outgoing Hawking radiation in subtle correlations that nobody has yet fully worked out. Others argue that information really is lost and that quantum mechanics needs modification. Still, others propose exotic solutions involving black hole remnants or wormholes or connections to other parts of the universe. The debate is not settled. It is one of the most active areas of theoretical physics today, with implications that reach far beyond black holes, into the foundations of quantum mechanics and the nature of space-time itself. For TON 618, the timescale for Hawking evaporation is so enormous that it is not really worth stating in normal numbers. It is many orders of magnitude longer than the current age of the universe. Ton 618, even if it stops accreting entirely and is left, alone will continue to exist for a time that dwarfs all of cosmic history by such a wide margin that for any practical purpose, we can consider it effectively eternal. The Hawking evaporation of Ton 618 will be completed long after the last star has burned out, long after the last proton has decayed in certain theories that predict proton decay, long after every structure we know of has faded into a cold, diffuse cosmic soup. Ton 618 will outlast the universe in every meaningful sense. This is a strange kind of durability. The stars will fade, the galaxies will disperse, the cosmic microwave background will redshift into insignificance, and yet the ultramassive black holes, the Ton 618s of the universe, will still be sitting there, slowly, patiently radiating away their mass, one subatomic particle at a time, waiting for a conceivable kind of eventual end in a universe that will long since have become dark and quiet. So when we call Ton 618 the heaviest shadow in the universe, we are also implicitly calling it the most enduring. It has already been here for at least 10 billion years. It will be here for many, many orders of magnitude longer than that. It is older than our world and will outlast everything in it by an unimaginable margin. And that brings me to a thought that I find both chilling and calming depending on the mood I am in. On any given night as I sit and look up at the sky, I am sharing a universe with Ton 618. Somewhere many billions of light years away, that object is, or was, or will be in a frame of reference that gets slippery the longer you think about it. In some sense, we are both here in the same cosmos, subject to the same laws of physics, each doing our thing. I, on a small planet, breathing, thinking, writing these words for you. It on the other side of the observable universe, sitting in vast and quiet grandeur, silently massive, the black heart of some distant quasar that shone long ago and may or may not still be shining today. We will never meet. We will never exchange signals. Our existences are so separated by time and space that in any practical sense, we will forever have been unknown to each other. But we share a universe. We are in that shared sense contemporaries, at least on the scale of the cosmos as a whole. And yet, when our time is done, when our sun has burned out, when our planet is gone, when human civilization has passed into the long silence, Ton 618 will still be there. Massive, dark, patient, continuing its existence on a timescale that dwarfs ours beyond comparison. If any future civilization billions or trillions of years from now looks out into the sky with telescopes of their own, Ton 618 will still be one of the largest things in their observable universe. They might have different names for it. They might have different theories about what it is. But the object itself will still be there, largely unchanged, silently bending space-time in its corner of the cosmos. This is the kind of object that teaches you perspective, not by any deliberate lesson, just by being what it is, just by existing at the scale at which it exists on a timescale that makes a human life seem, in comparison, like a brief flash of heat from a small candle. You cannot look at Ton 618 and hold on to any grand sense of human centrality in the universe. The universe contains things larger than us, older than us, more enduring than us, in amounts that we cannot easily count. And most of those things are quiet in the end. They are not performing for us. They are not sending us messages. They are simply being. And we, when we look at them, are briefly, gratefully included in the act of noticing. There is one more aspect of the limits of physics I want to mention before we begin to drift toward the close. It is the question of whether the classical picture I have been describing is really the right picture. As I noted, general relativity does not fully describe what happens at the center of a black hole. Quantum effects should matter there. And some recent theoretical work suggests that what we call black holes may not really have classical singularities at their centers, but instead might contain some kind of regular finite structure. Others have proposed that black holes might actually be made of a different kind of object, not singular at all, but very compact and nearly indistinguishable from the classical black hole at any distance we could observe. These are speculations, but they are serious speculations pursued by serious theorists, and they reflect the fact that our understanding of what is really going on deep inside a black hole is still incomplete. For TON 618, practically none of this changes what we can see. From the outside, the object is classical to a very high approximation. Quantum effects are imperceptible. Whether the center of TON 618 is a classical singularity, or a quantum-modified small region, or some more exotic structure we cannot tell, and will not be able to tell for a very long time. The outside of the event horizon behaves exactly as general relativity predicts. The accretion disk radiates as expected. The quasar shines as expected. The redshift of the light is exactly what Einstein's equations would have predicted. We have no reason to distrust our classical description of TON 618's exterior. But the interior, the realm past the horizon, is where the classical description reaches the edge of its validity. Beyond that edge, we do not really know what the universe is doing. We have models, we have candidate theories, we have beautiful mathematics, but we do not have anything we could reasonably call a complete understanding. And I think that is a perfect place to come to rest, at least for this part of the journey, because TON 618, for all the numbers and all the structure and all the stories we have told about it, ends for us at a boundary of knowledge. Not just a boundary of light, a boundary of understanding. We can look at it from the outside. We can measure its mass. We can pass its spectrum. We can theorize about its spin. But beyond the event horizon, we are in some real sense in the dark. Not metaphorically, actually in the dark. Our best theories fail us there. Our most careful observations cannot reach in. The deepest interior of the largest known thing in the universe is for now closed to us. There is a kind of peace in that. The universe does not have to give us everything. It has already given us so much. A species on a small planet can with patient work discover an object 10 billion light years away. It estimate its size, work out what it is made of, understand its physics to a limited but real degree, and share that knowledge with each other in stories like this one. That is enough for now. That is more than enough. The rest we can hold gently as mystery, as something beyond the horizon, as something that perhaps some future generation of thinkers and instruments will one day understand more fully, or that perhaps will always remain slightly beyond our reach. So we come to the end of the rules. Beyond this point, the rules stop applying, or at least our version of them does. And we turn for the last part of our drift toward what all of this ends in, toward the far future, toward the slow, quiet heat death of the universe and the place in that immense final quiet, where TON 618 will still be sitting, still dark, still vast, waiting, as it has always waited. Section 6, the final drift. We are nearly at the end of our drift. I want to use the remaining time gently. I want to let the shape of what we have talked about settle, and I want to look briefly toward the end of things, not in a sorrowful way, just in the way that any long, honest conversation with the universe eventually turns toward endings, because endings are part of the shape. TON 618, as we have said, will outlast almost everything. Our Sun has about 5 billion more years of main sequence life ahead of it, give or take, before it swells into a red giant, sheds its outer layers and settles into a quiet white dwarf that will slowly cool over trillions of years into a dim cold ember. The Milky Way, in about 4 or 5 billion years, will collide with the Andromeda Galaxy in a long, slow galactic merger, producing a single larger galaxy that some astronomers have playfully named Milkomeda. Over hundreds of billions of years, star formation across the universe will gradually wind down as the available gas is exhausted or locked up in long-lived low-mass stars. The last stars will burn out on timescales of many trillions of years. Then the universe will enter a long, dark age populated by slowly cooling stellar remnants and black holes. Through all of that, TON 618 will still be there. The ultramassive black holes and their smaller cousins will be among the last structures in the universe. As the stars fade, as the galaxies disperse, as matter slowly thins, the black holes will continue to exist, slowly evaporating through Hawking radiation, but so slowly that the process takes a number of years that we could barely even write down in any ordinary notation. Current estimates for the Hawking evaporation time of a supermassive black hole are on the order of 10 to the 100th power years. That is a 1 followed by 100 zeros. The current age of the universe in comparison is about 10 to the 10th years, a 10 followed by a 10 zeros. So the Hawking evaporation timescale for something like TON 618 is longer than the current age of the universe by something like 90 orders of magnitude. 90 orders of magnitude. If you doubled the current age of the universe and then doubled it again and kept doubling it for almost 300 doublings, you would still not reach the Hawking evaporation time of TON 618. Some numbers are hard to imagine. Some numbers at a certain point stop being numbers and become ways of gesturing at a kind of vastness that the mind was never designed to hold. The lifetime of TON 618 is one of those numbers. It is essentially forever by any meaningful measure. And so, as the universe settles into its late dim state with the stars gone and the galaxies dispersed, the great black holes will still be there, huge, dark, patient, continuing their existence on a timescale that dwarfs every other timescale we know. The universe will enter a period sometimes called the black hole era, in which these great dark objects are the most significant remaining structures. The cosmic landscape, once rich with stars and galaxies, will have simplified into scattered, isolated black holes, drifting through an ever-expanding and ever-thinning space. Some of them will very occasionally merge. Most of them will simply be alone in the dark, radiating Hawking radiation at temperatures so low that the quanta come out roughly one at a time, separated by eons of silence in between. Eventually, unimaginably far in the future, even the last of the great black holes will have faded. The Hawking evaporation will have completed. The mass of each black hole will have been converted one photon at a time over trillions of trillions of trillions of trillions of years back into the background radiation of the universe. The final faint glow of a once ultramassive black hole will be the universe's last spark of energy before the entire cosmos settles into the long, nearly empty stillness of heat death. But all of that is so far in the future that for us, it is essentially a story rather than a prediction. The universe as we experience it is still young. We live in the golden age of stars. We live in a time when galaxies are still full of light, when quasars like TON 618 are still in many cases burning somewhere, when the night sky, at least through a good telescope, is rich with structure. Most of cosmic history in terms of the slow settling into the quiet future is still ahead of us. We are in that sense fortunate. We are here early. The stage is still lit. We get to see. I want to end on that note because I think it is the most important thing. Not the Hawking evaporation, not the final heat death, not the 90 orders of magnitude. The thing I want to leave you with is the fact that we are here now and we can look. Human beings have learned to build instruments patient enough and sensitive enough and carefully enough arranged that the faint 10 billion year old light of an ultramassive black hole can be captured on a mountaintop, analyzed, understood, and then described in words to other humans in rooms where their eyes are closed and their breathing is slow. That this is a thing our species can do, that this is something our species has chosen to do, that this is one of the small, quiet, steady gifts we have given ourselves in among all of the noisier things. So sleep well. The stars are still burning. The galaxies are still turning. Quasars somewhere out there are still pouring out the light of their feasting light that will not reach us for billions of years. Anton 6-18, wherever it is now, is still their large, dark patient, holding in its vast interior 10 billion years of memories that we will never be able to read and probably would not understand if we could. If any of this drifted with you tonight, if any of it let you rest, that is enough. Thank you for being here. Thank you for letting the shadow of something enormous sit quietly next to you for a while. Thank you for letting the universe be strange and vast and old without asking it to be anything else. Somewhere in the dark, a monster weighs 66 billion suns. Somewhere in the dark, a photon is still traveling 10 billion years into its journey, aimed at a telescope that has not yet been built on a planet that will one day go the way of all planets. Somewhere in the dark space bends and time slips sideways, and light that will never return home keeps falling gently, endlessly into a silence we cannot cross. Sleep well. You are held. You are tiny, and the universe is enormous, and that is a kind of safety. Nothing out there needs you to be anything other than what you are. The quasar does not know about you. The black hole does not know about you. They will go on with their long, slow business regardless. And for a few hours before the world begins again, so will you. Good night. And thank you truly for drifting with us.